All right, continuing on after my coughing spell. Whew. All right. So the Doppler shift and transducer frequency. Another direct relationship. If the transmitted frequency is reduced to half, the measured Doppler shift will also be reduced to half. For example, a Doppler study is performed with a 2 megahertz transducer and the Doppler shift is 3 kilohertz. If the same study is performed with a 4 megahertz transducer, the Doppler shift, of course, doubles to 6 kilohertz. It only makes sense. It's just a simple, it's defining that relationship. Sound beam direction and flow direction. Now this is that interaction. In other words, if the blood cells are moving in this direction, how is my sound beam interacting with that, with the sound beam as blood, I hit the camera there, sorry. As sound is traveling this way, my sound beam is coming from this direction. It's that interaction. How am I picking that up? And I know you could see me through the little reflection there, but I've looked better. The measurement of the Doppler frequency depends on the relationship between the direction that the blood cell is traveling and the direction in which the sound wave propagates. When blood cells are moving parallel to the sound beam, the entire Doppler shift is measured. Blood cells are moving either directly towards or directly away from the transducer. And all that is saying is, if this is my sound beam, and I'm going to draw a little example here, whichever way I might be pointing it, and these are little red blood cells traveling, this is parallel. So if I have my blood cells traveling this way, my sound beam either strikes it and they're going towards it, or my sound beam strikes them and the red blood cells are going away. That is correct. Parallel. Everything is accounted for. And it is also 100% accurate. However, when an angle exists between direction of flow and the sound beam, the measured velocity is less than the true velocity. So the minute that you create, let me get my little tools here, an angle, the minute that you create that angle, okay, that sound is interacting with those red blood cells, that's when it becomes inaccurate. Or I should say, not inaccurate. I take that back. The measured velocity is less than the true velocity. With Doppler, you're going to learn that we set our standards based on a less than actual value because that's the best angle that we can get. There are more times than none we cannot get directly down the barrel of that lumen. So we have to set it, all the diagnostic indexes are set according to the best angle for ultrasound. So, you know, when you're looking at figure 19.6 and 19.7, that's basically showing the description of those, the angle of the sound and the angle, or the angle of the sound beam striking the moving cells. What is the cosine of 0? Now this is all just setting up the parts of that Doppler frequency, and it puts it all together. The cosine of 0 is the percentage, excuse me, went through puberty there for a minute. The percentage of the true velocity that is measured depends on the cosine of the angle between the sound beam and the direction of motion. Now, this describes basically the nature of the angle that we're striking that motion, okay? There's 0 all the way to 180. They call it cosine 0 because that's the best. That's the 100% most accurate because blood is moving towards us. So table 19.1 gives you the cosine angles. The registry and myself are only going to test you on these specific ones because that's the ones that we use in the field and that's the ones that are most important. And the others, they won't allow you to have a calculator, especially a scientific one. So just learn these and you will be fine. So 0 degrees is a cosine of 1.0 or 100%. So that is the most accurate. 60 degrees is a cosine of 0.5. That is 50% correct. 60 degrees is one of the end ranges of what we're going to learn when we get into the scanning of these things, and we're going to learn what degrees we should keep our Doppler angles within. So it's easier to say something to base numbers on 50% and double or cut that in half. It's easier to split up and figure out versus 0.87 or 0.69 or whatever it might be. That's why these numbers, these values are based on. That's why they chose those degrees. That's a little bit too deep, but that's okay. We can talk about that. 90 degrees, you have a cosine of 0 or 0. You get no flow. 180 degrees, which is on the opposite side of 0, is a negative 1.0 or a negative 100% accurate. The negative will just basically is hinting to you that blood's flowing away, which is a negative Doppler shift. When the angle between the direction of motion and the sound beam is 0 or 180 degrees, parallel to the sound beam, and the measured velocity is equal to the true velocity. Notice the 0 or the 180. They don't care if it's moving towards you or away from you. That measured velocity becomes equal to the true velocity. Excuse me. Think 100% accurate. A cosine of 0 degrees is 1.0, 100% accurate. Flow towards the transducer, that's a positive number. A cosine of 180 degrees is negative 1.0, 100% accurate, but the negative number shows a negative shift. It is flow away from the transducer. Everything starts at 0, so just however you just need to know this. It's easy if you think about it, draw it out. This is not difficult stuff. It's more intimidating than anything. Just learn your cosines, and any question they ask you, you'll be able to figure out what they want to know. So this cat over here is shooting his radar gun at this speeding minivan. Okay. Is he going to be 100% accurate? Absolutely, because her direction is coming right at him, and his sound beam is going right at, or his radar is going right at her. That's exactly the way it works. That's why you never see a cop standing on the side of the road shooting at an angle. He's trying to get as close to the direct line or a direct shot as possible, because that's the most accurate. Because if this happens, then this chick right here gives you a ticket and you can't fight it in court and you got to pay for it. When the direction of flow is perpendicular or 90 degrees to the sound beam, the measured velocity is 0. Because the cosine, remember, cosine of 90 degrees is 0. So this is perpendicular. My red blood cells are traveling to the right. That sound beam is going directly, cutting it in half. 0 velocity. Nothing else. Doppler signals and velocities cannot be measured with perpendicular incidence. So, this guy right here thinks that he has an app that can clock cars passing by. Well, if his beam is shooting from the back of this camera to these trees back here, and this car is going perpendicular to that, there is no way, it is physically impossible to get this number right here. This should be 0. Liar, liar, pants on fire. The cosine of 60 degrees is 0.5, or 50% accurate. Therefore, the measured velocity at 60 degrees is 1/2 the actual velocity. If red blood cells travel at 2 meters per second at 60 degrees to the sound beam, the Doppler reports the velocity as 1 meter per second. And that's okay, because that's what the basis of all diagnostic studies, that's the starting point, basically is dropped down to half of what the actual velocity is. Medicine is based on it as far as ultrasound. So all they did was just drop the starting point. So it's not like, well, why are we only half right? We're not. The foundation of Doppler is based upon being half right, and everything is just, every other number is knocked down from there. So non-directional Doppler. Ooh, did I do that right? Yep, okay. So that was the end of, excuse me, I had a little moment there where we talked about cosines, and I lost my way, and I wanted to make sure that I wasn't doing, I talked about everything, but I did. So please forgive my little TIA there. So let's move on to non-directional Doppler. Non-directional Doppler simply measures the presence of moving blood cells by detecting a Doppler shift. It does not distinguish direction of flow. It's just whether or not they're there. Example, blood is moving 2 meters per second. That's it. Hence, non-directional Doppler. Doesn't tell you which way it's going, it's just that it's there. It's used clinically where identification only is important. For example, excuse me, you have a post-surgical artery repair in a leg. Well, the doctor just wants to know if there's flow getting down there. He knows which way it's going. He just wants to know if it's there. It's not as important as if you're opening up a pathway. Say if they have, a blockage, or they get in a car wreck and the artery's severed and he repairs it. He knows it's going to go the right direction. He just wants to know if you hear it down by the foot, if he repaired it in the thigh. Heart patients, anything like that, they want to know that just the blood flow is there. They have Dopplers in the ER that patients will come in and nurses just feel for pulses in the feet. Well, I'm having leg pain. Well, the first thing you think is, okay, it might be a stenosis. Let's check for pulses. Well, we can't feel one. Let's get our little Doppler out and see if it's there. If they hear it, they're cool with it. If not, they call us in and we go look for it. Bidirectional Doppler, the most common clinical device. This distinguishes flow toward and flow away from the transducer. It has a direction of flow. Remember, positive is towards, negative is away. So it's bidirectional, towards and away, two directions. It's giving us that it's defining that for us. Bidirectional requires stereo headphones or speakers. One speaker represents flow towards, and one speaker represents flow away from the transducer. And it's kind of neat. It's kind of a very old school thing, but these old ABI machines that we just listen for pulses with, the right ear might be the one towards and the left might be the one away. It just worked then. The alternative to headphones is a Doppler spectrum, and that's what these machines do now. A spectrum displays this information graphically. In other words, we went from listening to we now have a baseline, and we can see what's going towards and away from the transducer. Everything above the line is towards, everything below the line is away. And we are going to talk about that in detail. So it's just a graphical thing. Flow towards the transducer is above the line. Flow away from the transducer is below the line. This is the line right here. Okay, might be hard to see, but towards, away, towards, away. That's the acceleration and deceleration of blood. It kind of starts, spits and sputters almost. If you would think about it that way, it's propelled and it slows and it almost backs up a little bit. Propels, slows, almost backs up a little bit. And that's just the nature of how we're built. Phase quadrature is a word you will see. All it means is that it's a commonly used signal processing technique for bidirectional Doppler. Simple as that. Machine does it for you. It's just a definition. Continuous wave Doppler. If you haven't noticed, we're starting to explain these Doppler processes a little more detailed. Continuous wave, you've heard this before. I know we've talked about it earlier. Now we're going to talk a little bit more detail in that it requires two crystals in the transducer. One constantly receives and one constantly transmits. So constantly transmitting, one's constantly transmitting, one's constantly receiving. Figure 19.9 shows that. It gives the picture. The yellow is the transmit beam, the red is the receive beam, and it kind of overlaps. And you notice where the overlap happens throughout the entire vessel. The advantage to this is the ability to accurately measure very high velocities. However, when you have that region of overlap happening right through the vessel, you're going to measure everything in that vessel. Okay? You don't get to pick and choose. You're measuring everything. So the disadvantage is its inability to determine the exact location of those moving red blood cells. Red moving blood cells. Huh. That's good. So we know that all blood cells, there's layers of different speeds, correct? So we're getting we're kind of at the limitation of, okay, we just get wall to wall and that's it. We don't get to pick if we want to measure right in the middle of the lumen where the velocity is the fastest. We're just limited with continuous wave. Signals arise from all red blood cells in the region of overlap between the transmit and receive beams. This is called range ambiguity. That is the disadvantage of continuous wave Doppler. Range ambiguity. It defines itself. The range is ambiguous. However you want to say it. It's almost like, all right, we're just gonna hope that whatever's traveling there is right, but we just look at it all and we jumble it all up. Here's the number. Figure 19.9 and figure 19.10. The velocities are measured over the entire sound beam. We just don't get to be selective. That's all. Continuous wave transducers are dedicated continuous wave transducers. That's another name, continuous wave or dedicated continuous wave. This type of continuous wave Doppler, now we're talking about the actual transducer that does it. The transducer contains only two elements. They're each shaped like a semicircle. So it's almost like they just shoved two crystals into a circular area, hence two semicircles. Look at figure 19.11. One, again, continuously transmit, and one continuously receives. These do not create images of anatomy. Continuous wave transducers do not create images of anatomy. Short duration pulses are then unnecessary because we only need that for imaging, correct? So it's the exact opposite of what imaging does. Continuous wave transducers do not need backing material, providing the following effects. Again, imaging transducers need backing material, and we know what happens when we use backing material. We'll just take away the backing material and reverse it. We have an undampened transmitted signal. We have a narrow bandwidth. We have a high quality factor, and we have a higher sensitivity. With imaging transducers that have backing material, all of these are reversed. So take the backing material away because we don't need imaging. Let the pulses ring. Voila. That's what you have. Very simple. Matching layers are necessary for obvious reasons. We still have to have that. All that does is increase the percentage of transmitted in and out of the body. We still need the bridge because the crystals are ringing. We still need the matching layer and the gel to get as much transmitted sound. Continuous wave transducers have have increased sensitivity. They can detect low amplitude reflections and small Doppler shifts. They're very, very sensitive. No different from a sense of taste or a sense of smell. If you have a heightened sensitivity, that's exactly what that means. These smaller Doppler shifts or low amplitude reflections, they can detect those much easier. Now let's talk about pulse wave Doppler. Only one crystal is necessary. The crystal alternates between sending and receiving. Hence the word pulsed. We have an on and an off time now, or a transmit and a listening. The sonographer positions a small marker or sample volume or gate. Let me read that a little bit better. Sonographer positions a small marker, a sample volume, or a gate. That's the two words. In a specific location on the 2D image. The ultrasound system then calculates the time of flight of sound pulse corresponding to the depth of that gate. And I'm going to draw you another little picture. You'll see this. That is what a sample volume or a gate looks like. And what we do is it's detecting, it's timing the time of flight to this point and back. Okay? Not here, wherever we put it. Okay? That's how we can be more specific to this. So if we have a stenosis, we can drop the sample gate right in the middle of the narrowest part of that stenosis because we know that's where the highest velocity is. So this is just an advancement, in other words. 1912 will show you pictures, very easy pictures of how we do this, and it actually has a stenosis. The transducer emits a sound pulse and then waits that exact time before briefly listening for a reflection. In other words, we put the gate out there and we time everything to that gate. If it's shallower, if it's deeper, and that's all going to make sense. We're not just sending it out there across both walls of the vessel and everything that comes back. We're being selective here to a select area. If the transducer receives an echo during this short listening time, the echo was created at that gate. See how they're using that top go return time? We know where the gate is. So if we receive any echoes within that time, then we know it was created at the gate. That has advantages and disadvantages. The advantage is the ability to select the exact location of the Doppler interrogation, range, Resolution. What does resolution mean? Accuracy. Range, resolution, range, specificity, or specific. This is easy as pie and straightforward learning advantages by knowing the terminology. The disadvantages are inaccurate measurement of high velocity signals. We're kind of limited when velocities get super high. High velocity flow in one direction is incorrectly displayed as traveling in the opposite direction or something that is called aliasing. And figure 1914 and 1915 show that, and I'll draw a little picture. If this is my limit and I have a very high velocity, and bear with me a minute, and this is the bottom of my screen, see how the top of the wave kind of wraps around the bottom? So I'm going past my limit here. Let me get this a little better. And I'm rolling up to the bottom here. That's aliasing. That's inaccurate. Because if I have my speed limit set to this, am I really telling the doctor exactly how fast it's going if I know that the waveform should look like this? So I can't tell him if this limit is 100. I can't tell him 100. It's maxed out. I have to take into consideration this down here because that's still part of the wave. And that should make sense, hopefully. If not, I will clarify it. I promise. Don't worry. Y'all are going to watch these videos 100 times and you're going to be sick of hearing my sick, disgusting cough voice. Aliasing or alias means false identity. So that's an inaccuracy. That's where the word comes from. Pulse wave Doppler. Pulse wave Doppler transducers. Since imaging and pulsed Doppler are created from pulsed ultrasound, then they can be performed with a single transducer. One transmit, one receives. Pulsed, short duration pulses. We can do both with these things. We can image and Doppler. Studies that simultaneously perform imaging and pulse Doppler are also called duplex examinations. Do we not have in this picture an image of what is the left common carotid artery? Do we not have a spectral Doppler down here, which we are a waveform Doppler that's giving us velocities? That is two different types of imaging at the same time, duplex. Pulse wave Doppler transducers are imaging transducers. They contain backing material. They have to be able to provide an image as well as Doppler a pulse. So, they have a low quality factor. They have lower sensitivity and wide bandwidth pulses. You know this already. You had a test on it and you all did good. You got this. Because we're all going back to what we used before. Backing material does all of this. Aliasing, as with high velocities, aliasing exists only with pulsed wave Doppler. Never with continuous wave Doppler. That's very important. I can ask you any question. Which of the following probes does aliasing occur with? Bam. What is the direct advantage which we talked about with continuous wave Doppler? No aliasing. So when the Doppler sampling rate is too low in comparison to the measured blood velocity, cells moving at high velocities are displayed as moving in the wrong direction. That wraparound effect that we showed, that basically because it's below the line, it insinuates that because it wrapped all the way around, that we have blood going in both directions. That is not the case. the waveform wraps around the scale and comes up from the bottom. There's something called the Nyquist limit. Remember the speed limit that I talked about earlier? That is exactly what this is. It is a speed limit. Aliasing occurs at any Doppler shift higher than this speed limit. So again, I'm going to draw a picture, and if I have my Nyquist limit set at whatever, let's just call it 250, and I'm going to draw a couple of waveforms here, so bear with me. So if I have my Nyquist limit set at 250, and this is my Doppler waveform, it cuts off here, right? I won't see this. Where does it show up? At the bottom. That is aliasing. So in theory, or actually in real life, this is what you see. Pardon my erasing. You see that wraparound effect. Can I report that as 250 centimeters per second? No, I cannot. I have to adjust this. And there's ways that we do it. And we're going to talk about that. But those waveforms or those velocities are exceeding my Nyquist limit that I have set. Figure 19.5. The Nyquist limit is the highest Doppler frequency or velocity that can be measured without the appearance of aliasing. Mathematically represented as the Nyquist limit in hertz equals the PRF in hertz divided by 2. I could give you any question in the world. Shanae's doing a scan on Candy's leg because it still hurts, and she needs to set her Nyquist limit. What is her Nyquist limit if she's imaging with a PRF of 10? 10 divided by 2 is 5. How simple is that? And that's the way the registry is going to ask. Anything about Nyquist limit, stick that little formula in your head, pull the card out, bam, take my free points, let's move it on. Deeper sample volumes create more aliasing. With pulse Doppler, velocities are assessed many times per second. The sampling rate of pulse Doppler is the system's PRF. It's a rate, it's a frequency. That's what the PRF is in Doppler. It's how many times we listen per second. Did I say that right? Yeah. Velocity, how many times we assess velocities per second. We have a excuse me. We have a shallow sample volume. The PRF is high. No different from anything else we've learned. Higher PRF. Velocity is estimated many times each second. The Nyquist speed limit is high. A system can accurately measure high velocities. So put this little scenario in your head. Shallow sample volume gives us a high PRF. The velocity is estimated many times. Our Nyquist limit is high. That's very important, okay? That means the system can accurately measure high velocities. We've set the speed limit high. Deeper sample volumes, we have a low PRF. The Nyquist limit is low. The velocity is measured fewer times each second. The system is unable to measure velocity, high velocities accurately. So we can't measure high velocities because the deeper we are, the lower our Nyquist limit, or the lower our PRF. You see where this is going. Lower PRF is associated with aliasing artifact. Higher frequency transducers create more aliasing. Now, right now you're thinking there's that shallow sample volume again, but if we put the sample volume, I'm not talking about, this has nothing to do with the frequency and the PRF being high. This is where we put something to listen, to go there and back at a shallower depth. Therefore, the times we're going to assess it is going to be much higher per second, correct? I'm talking about if I have a transducer that sends out a higher frequency, it is not related to this PRF. It is related to the frequency of sound I am sending out. Let's remember that. If you have to stop the tape and rewind it, stop it and rewind it, but understand that so that you do not confuse yourself. Higher frequency transducers create more aliasing because they create higher Doppler shifts. Lower frequency transducers create lower Doppler shifts. Just high, high, low, low. Therefore, lower frequency probes create Doppler shifts that are less likely to exceed the Nyquist limit, or aliasing artifacts are less common with lower frequency transducers. And that's the way you need to understand this, because that is very registry specific. These are just simple rules to follow. It is what it is, but because you have a past history with hearing all this, you should be able to easily grasp onto this and understand this. This is nothing all the way new. This is stuff that you can relate, that you've used before, to go, you should be saying, oh yeah, that makes sense. At least I hope you are. If not, please don't be concerned. I'll be back. We're going to go over all this stuff with a fine-tooth comb, and we're not going to test on it until we're ready. Okay? Because we're all going to be successful in this. Just grasp it. Just bear with it, and you're going to make it through it, and just learn the material. Table 19.2 shows the aliasing on page 307, and it just talks about defining it and the speed limit and all that good stuff. So I'm going to stop the tape here and continue on in just a minute. I'm going to take a little break and rest my voice, and I will be back. So we're going to continue with this table when we return.